Okay, good morning, and welcome to the next lecture of functional programming. So today we will do something that is only relevant for the master variant of this course, so for the V3M version. Namely, well, what did we do in the last lectures? We discussed the lambda calculus, and the goal was to translate Haskell to the lambda calculus. And you remember what lambda terms are? So lambda terms were a very simple language. Let's put it on the slide again. So it was this simple language of lambda terms. And so the syntax of this language was very simple. And the semantics is also very simple because we defined the semantics in an operational way by just defining alpha, beta, and delta reduction. And that's it. And we have seen that you can translate any Haskell program into a lambda term. And that in particular means that the lambda calculus can do as much as Haskell can. And in fact, it can do as much as any other programming language can. So it's a complete programming language. It suffices to implement any computable function. But now the question is it possible to reduce the lambda calculus even further? So, I mean, you might think that this is too much, too complicated. So can we throw away one of these lines and still get a complete programming language? And the answer is yes. And that's what we're going to do today. And in fact, this will be a short lecture, so we won't do the whole 90 minutes because of the re-accreditation of the computer science course. So we will stop at 11 or so, and then you can go home, or you can stay here, or whatever. But the lecture will not take the whole 90 minutes. So let's introduce a full programming language in 60 minutes or so. And the section is called the pure lambda calculus. So not this rich language that we have here, but the real pure thing. So the pure lambda calculus. So the question is, we know that the lambda calculus of the previous sections is a complete programming language. Sometimes one also says Turing complete because Church and Turing had the same goal. The question was, how can we formalize what is a computable function? And any language where you can express any computable function is called Turing complete. So the lambda calculus, like Turing machines or like any other standard programming language, is a Turing complete language, which means that we can program any computable function in the lambda calculus. We can program any computable function. And the question is, can we reduce the lambda calculus even further and still maintain Turing completeness? Can we reduce the lambda calculus further and maintain Turing completeness? And the answer is yes. And what we will modify is we will throw out the constants. So if you see these 4 lines of lambda terms, we drop the first one. So in the pure lambda calculus, the definition are just the last 3 lines. So variables are lambda terms, applications are lambda terms, and lambda abstractions are lambda terms. But we have no constants anymore. That's the pure lambda calculus. And so the answer is yes. And that's the pure lambda calculus. And how does this result from the lambda calculus? Well, it's the lambda calculus without constants. And so that's the syntax. And what's the semantics? Well, up to now, we evaluated terms by beta and delta reduction. Now, delta reduction makes no sense if we have no constants, because delta reduction tells us what happens if we have a term that starts with a constant. But if we have no constant, then delta reduction is not applicable. So the only way to evaluate pure lambda terms is beta reduction. So this is the syntax, and the operational semantics is just beta reduction. So just beta reduction, nothing else. So delta reduction is no longer applicable if we have no constants. It's no longer applicable. And so the surprising observation is this is still a complete language. This is not going to result in very readable programs, but that's not the point. I mean, a Turing machine also doesn't result in readable programs. The point is, how restricted can the language be and still be a complete language? And that's, well, the observation is this is still enough. So let's try to illustrate this. How can this work? So now we have just this pure lambda calculus without constants, and now let's try to program something in this strange language. For example, let's try to program some algorithms on numbers. Now, let's look at some examples. So, algorithms on numbers. Let's say on natural numbers to make life a bit easier. Now, up to now, as long as we had constants, the natural numbers were not a problem because, well, we just added all the numbers in the set of constants. So the set of constants here, it contained 0, 1, 2, 3, 4, and so on. Now we have no constants anymore. So we have to represent the numbers by lambda terms. This, I mean, that's not going to be extremely readable, but we simply have to fix some representation. By which lambda term do we want to represent the number 0? By which lambda term do we want to represent the number 1? This is something we have to fix, and then we can write algorithms operating on these numbers or in these lambda terms that represent the numbers. So now we have to represent numbers by lambda terms because we have nothing else in our language. We have to represent numbers by pure lambda terms. And so how do we want to represent the number 0? And I will denote the representation of the number by writing a bar above it. So 0 bar, this should be the lambda term that represents the number 0. So what should be the representation of 0? And what should be the representation of 1? And what should be the representation of 2? And so on. And, well, there are several possibilities how to represent this. And one possibility is we could try to represent a number n as the n times application of a function. So the idea is represent a number n. So any number n should be represented as the application of a function to an argument n times. As the n times application of a function f to an argument x. So as something like this, f of blah 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 of f of x n times. Now, in this way, we could represent the number n. And of course, the name of this f is also just a variable. The name of this variable f and the name of this variable x, they shouldn't really matter. So since these names play no role, so since the names f and x, they do not really matter, let's abstract from these names and just add a lambda in front of it which binds f and x. So we could write lambda fx, and now this fx n times. So that's the idea. This will be our representation. So the representation of a number n will be the lambda term lambda f and lambda x dot, and now f applied n times to x. Now this doesn't look nice, but that's not the point. The point is this a machine language which is powerful enough to express computation? So if we represent any number n by this term, then what would be the representation of 0? It would be the term lambda fx. So it's the function that takes an f and an x and applies f 0 times to x. Okay, so it's just x here. And what's the representation of 1? It's the function that takes an f and an x and applies f 1 time to x. And what's the representation of 2? It's the function that takes f and x and applies f twice to x. Okay, so in this way we could represent any natural number. And now the claim is with the lambda calculus, with the pure lambda calculus, I can implement any computable function. No, this is wiped so badly. And of course, writing programs in the pure lambda calculus is tedious, so we will not implement too difficult programs. So let's start with a not so challenging program, the successor function. So the successor function is the function that takes a number and increases it by 1. And this is clearly a computable function, so I should be able to write it in the pure lambda calculus. Okay, so now the goal is write programs in the pure lambda calculus, of course. In the pure lambda calculus that operate on numbers. And when I write numbers, I mean this representation of numbers that operate on this representation of numbers. Representation of numbers. So, for example, we might want to write a program suc. So this is the representation of the successor function. And what should this do? It should take a number, n, and compute the number n plus 1. Now that sounds trivial, but in the pure lambda calculus, nothing is trivial. So what should happen? If I apply this to the representation of n, then this should be, if I start evaluating it, and evaluating means beta reduction, because that's the only evaluation that I have in pure lambda calculus. So if I start evaluating this with beta reduction, I may do this in several steps, then in the end, I want to get n plus 1. And, well, I mean n plus 1 represented as a lambda term. So in other words, this suc bar, this should be some lambda term. And if I apply this to this lambda term is lambda fx dot f applied n times to x. This is the representation of the number n. If I start evaluating this, then I want to end up with n plus 1. And what is n plus 1? Well, it's the term lambda fx, but now f is applied n plus 1 times to x. Okay, and now programming in this language means I have to come up with a lambda term that does this. Now, even if you're an experienced programmer, this will be challenging if you never did this before. And of course, writing very sophisticated programs in this language is no fun. But writing this kind of program is fun, I hope. So, okay, let's try to come up with something that does this. And well, to have an idea how to come up with a lambda term that does this, one possibility is to try to transform this desired result in such a way that it contains the argument. So to find a lambda term for suc, we can try to transform the desired result, so this thing. We can try to transform the desired result, so n plus 1, in such a way that it contains the argument. Such that it contains the argument, because then we can see what this lambda term has to do. So let's try to do this. So n plus 1. What is n plus 1? Well, it's this term here. So it's lambda fx, and then f applied n plus 1 times 2x. And I want to transform this term in such a way that I get this term as a subterm somewhere. Now here I have n plus 1 applications of f, and I want n applications of f. So clearly I can rewrite this in the following form. I can write, well, this is f applied to f applied n times to x. So this looks already better. And now this is not quite n bar, but how could I get from n bar to f applied n times to x? If I have this term and my only evaluation is beta reduction. So how can I get from this term to this term? This is a function. Right. Well, make a new function. I cannot give names to functions since I have no constants. But indeed, apply this function to appropriate parameters. And what are the appropriate parameters? So this is, I can get this by applying n bar to the following arguments. To which arguments do I have to apply it? Well, to f and x. If I apply n bar to f and x, then I get the body of this lambda abstraction, but all occurrences of f are replaced by f, and all occurrences of x are replaced by x. So nfx, this really reduces to f applied n times to x. So this gives me the idea. So now I see what I should do. If I apply suc to something like this, if I apply suc to some argument like this, then what this should do is it should return lambda fx, but then apply the argument to f and x. So this should give me lambda fx, but then here I should have f, and now I should apply the argument n to f and x. So this is what I want. And if this works, then everything is fine. If suc applied to n bar would give me this, then everything would be fine, because then n bar fx would reduce further to f applied n times to x. So in fact, for any argument, if I apply suc bar to it, it should give me this result. So for any argument, for any term n, I would like to have suc of, or let's not say n. For any argument g, I want that suc of g rewrites to lambda fx g fx. So if suc does this, then everything is fine. And what is the solution? So which should be the lambda term? Suc? Well, it should be a lambda term such that if I apply it to g, then it gives me this. So the only problem that is left is I have to bring this g from the left-hand side to the right-hand side. So it's lambda g fx dot, here I forgot something. I forgot the f here. So it should be f and then g fx. So it should be lambda g fx and f applied to g fx. This is the successor function. Now, this is in no way readable. I mean, if you see this, then it's not immediate to recognize that this is the function which increases a number by 1. But it does what it should. If you don't believe it, then just execute it. So let's test. Suc of n, what is this? Well, suc is this thing here. It's lambda g fx dot f g fx applied to n. So this is suc bar. And what is n bar? Well, n bar is lambda fx dot f applied n times to x. And the only evaluation that we have is beta reduction. So if I do beta reduction, then this means I have to replace all occurrences of g by the argument. So the result will be lambda fx dot, and now I have f of g fx, but g is replaced by the argument. So lambda fx dot fnx fx. And if I apply beta reduction 2 more times, then all occurrences of f here are replaced by f, and all occurrences of x here are replaced by x. So I have lambda fx dot f and now fn times x. So this is fn plus 1 times x, and this is n plus 1 bar. So indeed, this computes the right thing, even if it doesn't look too readable. And, well, suc is, of course, a very simple function, but if you are ambitious, you can also write algorithms for addition, multiplication, factorial, whatever you like. And these, of course, will be even more ugly-looking lambda terms, but it works. So after we've seen that this works on numbers, let's look at some other data types. Let's, for example, look at the Booleans. How would we implement algorithms on Booleans? Because plus and times are really complicated. Let's look at something more simple. So the next example is, let's realize the Booleans. So again, the only syntactical object that we have are lambda terms, and the Booleans, they have there are 2 Boolean objects, true and false. So we have to represent true and false by appropriate lambda terms. And of course, there are many possibilities, but let's take one which makes the formulation of algorithms easy afterwards. So which lambda terms do we take for true and false? Well, my proposal is for true, we take a projection function which takes 2 arguments, x and y, and it returns the first argument. So this is the function that takes 2 arguments, and it gives you back the first argument. And then false is the function that takes 2 arguments and gives you back the second argument. Yeah?
How do you implement a function that decrements the number by 1?
Yeah, that's no fun. You have to think about this. I cannot tell you immediately, so I would have to think about it as well. So it's possible. And if you spend enough time, you will come up with a solution, but it will not be, it's not that easy. So I don't know by heart. And I won't construct this now from scratch because then the lecture will be over before we solved it, most likely. But it's possible. OK, now true and false. Now, what can we, which algorithms do we have on Booleans? Well, things like and or and so on. And in particular, if then else. I mean, that's one of the things that we need in the lambda calculus, because if you remember, when we translated Haskell to the lambda calculus, we added some built-in constants. We added a built-in constant if, which does if then else, and we added a built-in constant fix, which computes the least fixed point. And when I claim that you could do this also with a pure lambda calculus, then in particular we should be able to implement if and fix also in the pure lambda calculus. So let's implement if. So what is if? So what should if do? Well, the goal is if I apply if to true and to two more arguments, let's say u and v, then this should reduce to u. And if I apply if to false and uv, then this should return v. That's the semantics of if. It's if then else. So if this is true, then you get the result of the then argument, and if it is false, you get the result of the else argument. So the question is, how could a lambda term if bar look like that does this? That's not so difficult. That's much easier than suck. So you can think about it while I wipe the remaining boards. Maybe you can come up with it. It's pretty easy. So any solutions? Yes?
It is lambda buv dot buv.
I need to write this down. So the proposal is the following. Lambda what?
buv. B for some boolean.
Let me write z because z we did it.
Okay. And u and v.
Sorry?
uv, so arguments. Yeah. Dot zuv.
Okay. Okay, let's see whether it does this. So what happens if I apply this to true uv? So this will, so this, it's correct, but it can be done even simpler. But you're right. So this will be applied to true u and v. So z is instantiated by true, u by u, v by v. So we get true applied to u and v. And what is true? True is lambda xy dot x. So this is applied to these two arguments, and it selects the first one. So indeed, this of course rewrites by beta reduction. And by two more beta reduction steps, I indeed get u. So indeed, this is correct. And for false, it works as well. Because if here you would have false, then you would apply the selection function to u and v, and you select the second argument. So indeed, it's correct. And you can do this even easier. So if you drop u and v here and there, it would do the same thing also, because now it would be the identity function, which needs only one argument. So both solutions would be fine. So indeed. So the identity function is already enough. And it works so nicely because we use this encoding for Booleans. So this encoding is particularly suitable for implementing the if function. But you can also implement all other functions with this encoding. So yes, indeed, it works. So you get more and more experienced in programming in this language. And I mean, when you think of the programming comfort that you have with programming here, you should compare this with programming in Turing machines. So if you program successor or any other function in Turing machines, this is also pretty tedious. And so that should be the level of comparison. But the difference to Turing machines is that the lambda calculus is not only a theoretical model, but it can be used as the basis of real programming languages. And I mean, the connection between lambda calculus and Haskell is pretty obvious, because it's really a subset of Haskell. I mean, all these lambda terms you can write in Haskell, and Haskell just has some more syntactic sugar to make programming more fun. But so this has really some practical applications, whereas Turing machines have not so much practical applications. At least I'm not aware of a practical programming language which builds upon Turing machines. And here this is indeed possible. OK, so we are now convinced that we can program this if in the pure lambda calculus. Now, what else did we have when we implemented Haskell? I mean, we used all these predefined constants, like a predefined constant for if, a predefined constant for fix, and we also needed some predefined constants to recognize constructors or tuples and to select or to get the arguments from constructors or tuples. So could we do this also in the pure lambda calculus? So can we also implement things like functions like is a constructor or is a tuple, is an n tuple, or these selection functions like arc of constructor, or select the ith argument from a tuple with n components. Can we implement things like this also in the pure lambda calculus? And well, if it's a Turing complete language, then this should be possible. So of course the answer is yes. And let's do one example. Let's do the selection function. So what's the goal? Let's try to implement these selection functions. So what should these selection functions do? They should take a tuple with n components and return the ith component in this tuple. Now, can we do this in the pure lambda calculus as well? So what we want is, we want that if you apply this to a term built with, well, in the lambda calculus, we have no tuples. So to represent tuples, we used a special function symbol. So something like this, tuple n. And if this is applied to arguments t1 to tn, then this should return ti. This works in the full lambda calculus. So how do we do this in the pure lambda calculus? Now, first of all, we have to find representations both for this constant and for this constant. So in the pure lambda calculus, we don't have constants. We have no constants, and therefore we have to replace this constant and this constant by appropriate lambda terms. So tuple n and cell ni have to be replaced by appropriate or by suitable pure lambda terms. And so let me give a representation of tuples, and then we can think about how to implement the selection function. And again, to represent data structures, there are many different possibilities, but once we fix the representation, then we can try to program algorithms on these data structures. So let's say tuple n. What should be the representation of tuple n? Well, a tuple n we represent by, well, essentially applying a function to n arguments. So this should be something like we apply some function f to n arguments, x1 to xn. Now this looks similar to a tuple with n components. And of course the names of f and x1 and xn, they should play no role. And so we abstract from the names again. So let's add a lambda in front, and then we abstract from x1 and xn and from f. So let's take this representation. So this means an n tuple is represented by applying a function to n arguments. And then the question is, what is cell Ni? So by which lambda term would we represent this? And, well, again, the goal is clear. So the goal is, if I apply cell Ni to a term of this form, tuple n, and then apply to n arguments, then this should reduce to the ith of these arguments. So this is the goal. And the question is, how does this lambda term have to look like so that it works? So what is this? This is tuple n applied to z1 to zn. So this is tuple n is this lambda term, lambda x1 xnf dot f x1 to xn. And this is applied to z1 to zn. Now, of course, this you can simplify by beta reduction, because this just means x1 to xn, they are instantiated by z1 to zn. So this can be simplified to lambda f dot f z1 to zn. So in other words, it would be enough for us if cell does the following thing. If I apply this to this thing here, so to lambda f dot f z1 to zn, then I should get the ith component in here. So how can I come up with a lambda term that does this? If I apply this lambda term to this, then it extracts the ith argument here. Now what is this? This is a function that waits for an f, for another function f. And if f is there, it applies f to these n arguments. Yeah?
So then we should just take the representation of the tuple and apply a function or lambda term that takes n arguments and returns the I.
Right. Exactly, exactly. So we should, so the goal indeed is we have to take a lambda term that takes n arguments, and it returns the ith argument. So this is this projection function which takes n arguments and gives you the ith argument. And now what should we do with this lambda term? Right, we should apply this thing to this. Because if we apply this thing to this, then this f will be instantiated by this function. And that's the projection function to the ith argument. So if I apply this to this, I get indeed zi. So that's a very good observation. And this shows me what cell Ni should be. So cell Ni should be a lambda term that takes its argument. Okay, so if it gets some argument g, so some argument g like this, then it should take this g and apply it to this projection function. So it should take this g and apply it to this projection function. Lambda y1 yn dot yi. Okay, so now I know how this lambda term looks like. Cell Ni is the lambda term that waits for a function g and then applies g to lambda y1 to yn dot yi. So that's the solution, and if you don't believe, you can check. So indeed, if I take cell Ni and I apply it to, what did I want? Tuple n z1 to zn. Then what is this? Well, it's this function here. So it's lambda g dot g applied to the lambda term y1 to yn dot yi. So this is cell Ni. And this is applied to tuple n. Tuple n was lambda x1 to xnf dot f x1 to xn applied to z1 to zn. So this is tuple n. And now this can be simplified to the following thing. This remains unchanged. Lambda g, lambda y1, yn dot yi. But this can be simplified by beta reduction. So I instantiate the x's by the z's. And then I have lambda f dot f z1 to zn. And now I do another beta reduction step, and I instantiate the g here by this lambda function. So I do one more beta reduction. And now I have lambda f dot f z1 to zn applied to this thing. Applied to lambda y1 yn dot yi. And now I do one more beta reduction, and I replace this f by this function over here. So I have lambda y1 to yn dot yi applied to z1 to zn. And by further beta reduction steps, I then get zi. So it does the right thing.
One question, why do we use this encoding for tuples and not just say, oh, tuples are these z1 to zn and then use this projection function directly as a selection function?
Well, the question, so what we want to have is we want to encode all the constants that we had up to now by lambda terms. So we need an encoding for tuple n, and we need an encoding for cell Ni. So what would you propose as encoding for tuple n?
Not encode it in a lambda term at all, but just use the arguments. Just use the components of the tuple as arguments for the function.
Well, then it doesn't do the same thing as here, because what I wanted was I wanted to replace the constants that we had up to now by lambda terms. And we had a constant tuple n up to now, and we had a constant cell Ni. And of course, you can also write different functions where cell Ni takes n arguments directly and gives you back the ith component. Then it would be just this term here, which you need. But here the point was I wanted to show that you can do without the constants. So the constants that we had up to now can be replaced by lambda terms, and it still does the same thing. So one more example, one last example. Now probably the most challenging constant that we had when we translated Haskell to the lambda calculus was the constant fix. And well, this fix we need whenever we want to implement functions defined by recursion. And of course, well, that's everyday life. If you program in Haskell, you program by recursion. And so the question is, can we also implement recursive functions in the pure lambda calculus? So to implement recursive functions, so functions defined by recursion, up to now we translated them into a lambda term containing the constant fix. Up to now, we translated them to a lambda term with the constant fix. And then we've seen that this lambda term does the same as the original recursive Haskell function. So now the question is, can we do this also in the pure lambda calculus? So the question is, can we also implement this fix in the pure lambda calculus? And this fix is the function that computes the least fixed point of its argument. Well, we should be able to do so because everything that can be done in the full lambda calculus can also be done in the pure lambda calculus. The only question is how. So what should be the goal? Well, up to now, if we had the constant fix, then what could we do? If we apply a fix to some argument, then this could be evaluated to z of fix z. And the meaning was that, well, you should think of z as a function, and then fix z is the least fixed point of this function. So if fix z is the fixed point of z, then it shouldn't matter whether you apply z to its fixed point or you take the fixed point directly. And we used this evaluation in order to implement Haskell. So this was how we did it up to now in the full lambda calculus. And in the pure lambda calculus, we need some lambda term instead of this constant. So we need some lambda term fix bar, but it should do the same thing. We need a lambda term fix bar, which has this behavior. And the question is, how could such a lambda term fix bar look like? And well, constructing this is no fun, so I will give it to you, and you don't have to construct it yourself. And there are different variants of this, so many lambda terms satisfy this. And the easiest one is probably this one. And this is called the fixed point combinator of Turing. So maybe Turing discovered this, I don't know. So it looks ugly, as expected. So it takes lambda, x, and y. And well, one thing you can see here is that this fix leads to non-termination, because I can clearly apply this beta rule forever. Now, if you want a non-terminating lambda term, we have seen one already, then the main idea is you need self-application. You have to apply something to itself. That typically leads to non-termination. So this is also happening here. So we apply y to some strange argument, and in this argument, x is applied to x, and the result of this is applied to y. And since this is not ugly enough, we apply this whole term to itself. So we copy this thing once more. So lambda xy dot y xxy. So what this expresses, we have no intuition. I mean, I have no intuition what this says. And so to come up with this is pure fiddling around, I would say. But checking whether it does the right thing, that can easily be done. So my claim is that this does the right thing, or in fact Turing's claim is that this does the right thing. So we don't know how he came up with this term, but we know how to check it. So let's check whether he did it correctly. So fix z, what's this? That's applying this ugly thing to, okay, this thing applied to itself, lambda xy dot y xxy, and this thing applied to z. And the hope is that this will return, so this is fix. This thing here is fix. So let's check whether it does what it should. So lambda xy applied to this. So we need to instantiate the x by this term and the y by z. So let's do this. So we do two beta steps at once. And then the y has to be instantiated by z. So we have z. The x has to be instantiated by the thing over there. So by lambda xy dot y xxy. This x has to be instantiated by this term as well. So lambda xy dot y x xy. And the y has to be instantiated by z. And then if we look at it, we see, aha, this is again fix. So indeed, this is z applied to fix z, which is what we wanted. So yes, we can check that it does the right thing. And so this indeed computes the same thing as our constant fix. It is not readable, but it does the right thing. So the remaining question is, since the pure lambda calculus is enough, why didn't we use it? So why did we have these constants? We could have translated Haskell directly to pure lambda calculus. For an implementation, readability plays no role because the computer executes this, and the computer won't complain that he cannot read this, because, well, the computer can read anything. So why do we translate, if we want to implement Haskell to full instead of pure lambda calculus? Instead of pure lambda calculus when implementing Haskell. So the translation to pure lambda calculus would be possible. Instead of the constant fix, we use this term, and instead of all these other constants, we can also use appropriate lambda terms. So do you have any idea why we didn't do it? Because it's harder for the students to read? Yeah, okay, that's one valid answer maybe. But there's one really convincing answer. So another reason could be efficiency, because maybe the implementation in the full lambda calculus is more efficient because one of these delta rules subsumes several of these beta reductions that we would have to do in the pure lambda calculus. So yes, maybe our translation is more efficient than the one to the pure lambda calculus. But there's one even more convincing reason. And the problem is, well, if you implement Haskell, if you think of your Haskell compiler, what does it do? If you write your Haskell program and then you want to run it, does it run it directly? No. It first does type checking. So it first checks, is this thing well typed? And only if it is well typed, it will execute it. And so, I mean, we want to write a Haskell implementation as well, so our implementation should do the same thing. So our goal was, we want to translate Haskell first to lambda calculus, then do type checking, and then execute it. So we want to do the following thing. Translate Haskell to some machine language, so to the lambda calculus. So then we get a lambda term. Then we do type checking. And only if this type checking works out, only if this thing is well typed, then we execute this lambda term by beta or beta and delta reduction. So execution by beta reduction, or if we have full lambda calculus, then by beta delta reduction. So if this is our goal, then you can probably find out why the pure lambda calculus is unsuitable. Mm-hmm.
All constants will be replaced by lambda terms, and it's always well typed.
Well, some constants, some lambda terms for the constants might be well typed, but this one is not well typed. So this one is not well typed because we have these self applications here, and I have already mentioned in an earlier lecture, as soon as you have a non-terminating lambda term, so without constants, then this thing is not well typed because the type lambda calculus on its own would be terminating. So as soon as we have a recursive function, this will be translated into a pure lambda term that is not well typed. And so type checking makes no sense anymore because any well typed Haskell program is translated into a lambda term which is not well typed. So we get non-well typed lambda terms all the time, and so type checking makes no sense anymore because it would fail all the time. So this would not work when translating to pure lambda calculus. To the pure lambda calculus. Because terms like fix, bar are not well typed. So this means I would translate every recursive Haskell function into some lambda term containing fix bar, and fix bar is not well typed, and so type checking would fail all the time. And then, well, we cannot do type checking on the lambda calculus anymore. So that's the main reason for using constants instead of the pure lambda calculus. And, well, how to do type checking on the lambda calculus, that's the remaining question that is left open. Well, that we will solve in the beginning of July when the lecture continues. So the next week, there will be no lecture. There will be exercise course on Monday and Friday and nothing on Wednesday. And the week after, we meet again on Monday, and then I will tell you how to do type checking. OK, so see you then.